Okay, so now for this second part of this example, like we showed in the last video towards the end there, finding the representation of this vector as a coordinate vector relative to s prime, our standard basis, is very straightforward, as it always is anytime we're working with a standard basis. In this case, the coordinate vector literally just looks like the coefficients of this polynomial. But again, if we choose a different basis, that can look drastically different. So illustrating that, we're going to use this new basis here. In the basis s, how do we take this polynomial, 1 minus 2x plus 4x squared, and write it as a linear combination of those three vectors, which we're guaranteed to be able to do because, again, it is a basis. We're not proving it. We're just taking that for granted here. Now, in the previous example, when we were working in R2, we were able to find the linear combination that we needed kind of just by inspection. We just thought about it and we said, well, you know, this one scalar here, this would have to be a 3, and that would imply that the other one has to be a negative 1/2. It's fairly easy to see that. It's a lot harder to take that approach here. You can still probably do it if you think about it, but we're going to take a more broad or general approach with this that'll work for any similar example. So what I'm going to do is say this has to equal some linear combination of those vectors. So I'm going to use k1 times the first vector in that set plus k2 times the second vector in that set, 1 plus 2x, plus k3 times the third, 4x squared. Okay? Now, what I'm going to do is imagine multiplying each of those k's in and combining like terms, and then setting the constant term on this side equal to 1, the linear coefficient on this side equal to -2, and the quadratic coefficient equal to 4. Okay, and that's going to create a system of 3 equations. So let's start with the constant term. On this side, my constant term is going to look like k1 plus k2. So k1 plus k2 is going to equal the constant term on this side, which is a 1. Okay, and then my linear term, I'm going to get a negative k1 here, a 2k2 over here, and nothing from this side. So that's going to look like negative k1 plus 2 equals the linear coefficient -2. And then I'm going to use my quadratic terms for my quadratic coefficients. There's no quadratic terms in either of these first two cases, so the only coefficient I get is the 4k3. So 4 times k3 equals the coefficient here, which is also a 4. Okay, let's make an augmented matrix out of this. So this is going to look like 1, 1, 0, 1, -1, I forgot my k2 over here, 2, 0, -2, and then 0, 0, 4, 4. Okay? This matrix is fairly easy to do Gauss-Jordan on, but again, to save us time, you know how to do Gauss-Jordan. I'm just going to take us straight to the result. So after doing Gauss-Jordan, I'm going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. And then over here, I end up with 4/3, -1/3, 1. That is my coordinate vector right there. Because remember, the unknowns were k1, k2, and k3. This is the solution that I get. And so this would be the scalars which make up my coordinates. And again, we think of this as an ordered basis. So even though as a set, there's technically not a prescribed order in the general case, here we're actually thinking of this as vector 1, vector 2, and vector 3, so that these coordinates should be written in this exact order. That means the coordinate vector for P relative to S looks like 4/3, -1/3, 1. Okay, and again, remember, even though the exact same polynomial has different coordinate vectors, that's only because these represent the scalars in different bases. Okay, so they can look different, but they represent the same vector because we're talking about a different coordinate system. All right, last thing I want to do here is a theorem that I mentioned in an earlier video from this section, and we're going to prove this now. This theorem, I believe, actually shows up in section 4.6 in your book, but I like introducing it here because it kind of wraps things up in a really useful way that segues into section 4.6 a little better. So V is going to be a finite dimensional vector space, which, remember, there exists some finite spanning set for that vector space. That's what that means. And it's going to have the following basis, V1 through Vn. One thing I didn't say previously, and you probably didn't even think to question this yet, just because this is a new concept, but I never said that every vector space has a basis. You know, nothing that we've done so far necessarily rules out the possibility that a vector space can exist such that there is no basis for that vector space. But that doesn't turn out, that's not the case actually. It turns out that every vector space, whether finite dimensional or infinite dimensional, will always have a basis. And that's one of the fundamental theorems in linear algebra. We don't prove that explicitly here, especially because when we open things up to the infinite dimensional cases, it just extends a little bit beyond the scope of this class. We need to talk about set theory, something called Zorn's lemma. It's worth looking up if you're interested. But we're going to take for granted the fact that every vector space does in fact have a basis, which allows me to say this. Okay. Now, we've established that we have a vector space with a basis containing these n vectors. And now I'm going to let S be just any other set of m vectors, different from n, m. So if S is just some subset of V containing m vectors exactly, then the following two things are always true. If m is greater than n, in other words, if this set has more vectors in it than this basis, then this set is guaranteed to be linearly dependent. I mentioned that in a previous video, but here it is in the form of a theorem. If m is less than n, if this set has less vectors than some basis for V, then S will not span V. Now we're going to prove part A of this. Part B follows a similar thought process, so I'll just talk a little bit about it without proving it. But I want to point out what this means, and I'll mention it again in section 4.6. These two conditions need to be in place if a set is going to be a basis for a vector space, right? The only reason V1 through Vn is a basis is because it's both linearly independent and spans V. So what this is telling us is that if you have some other set of vectors that has more vectors in it than a basis for V, then it's not a basis because it's linearly dependent. Similarly, if any set in V has less vectors in it than a basis, with, you know, in this case n vectors, then it's also not, this can't be a basis because it won't span V. What that means is that in this case, if V has this basis with these n vectors, then any other basis for the vector space V would also have to have exactly the same number of vectors. Otherwise, it's going to lose one of those defining characteristics of a basis. Okay? Now, that said, we also need to be careful. What this does not say is that every every set of n vectors is a basis for V. This doesn't mean that any set of n vectors would be a basis for V. I could very easily find other sets that are not. It just says that if a set is going to be a basis, then we can always be sure that it will have n vectors in it. Okay, so enough of that. Let's get into the proof. So again, basis is going to be the V's, V1 through Vn, and the set S is going to be these W's here, W1 through Wm. Let's suppose that m is greater than n. We have more vectors in this set than we do in this basis. The goal here is to show that this set is linearly dependent. So this is going to follow steps that resemble something we've done previously. It might look a little bit familiar. Because this is a basis, the V1 through Vn forms a basis for S, every vector in V can be written as a linear combination of those, because this would have to span V. In particular, all of the vectors in S can be written as linear combinations of those V's, which we've done here. Okay? So this can, for some set of scalars, you know, a's, all of these a's here, this will end up being true. Okay, now what I'd like to do on this next page here is take a look at a linear combination of the w's and set that equal to 0. Remember, the goal here is to prove that this is linearly dependent. And to do that, I would have to show that this equation has non-trivial solutions for these k's. So I've created this linear combination and set it equal to the 0 vector. But what would that look like? Well, remember, we've taken all of our w's and represented each one of them as these linear combinations of the v's. So for each linear combination, I'm taking that and plugging it in for the corresponding w over here. This w1 is going to turn into this big giant linear combination. This w2 is going to turn into this linear combination. This guy right here. So this is going to get very, very big and messy. My first term is going to explode into this. Notice that the k1 would have distributed into every term of that linear combination, which is why we see k1s everywhere. Similarly, this k2 will distribute in, and we get this. And then all the way down until I get to the km, that distributes into that linear combination. And the sum of all of these, notice I'm adding everything, is equal to the 0 vector. Okay? But like we've done in that previous example that I referenced, because this is a sum, a gigantic sum, and because vector addition is commutative in vector spaces and associative, I can rearrange all of the terms and group them however I want. That means I can choose to add all of the v1 terms together, all of the v2 terms together, and group those, you know, appropriately. So if you notice the coefficients on my v1s, k1, a11, k2, a12, if I added those vertically, this is what I would get, k1, a11 plus k2, a12 plus everything until I get to this last coefficient here. That would be the coefficient on the v1 if I grouped things that way. Similarly, I could group up my v2s and all the way through my vn's, okay? And that's equal to the 0 vector. Now, with that said, what I've just done is I've taken this big mess and represented it as a linear combination of the v's. Notice it's a scalar times v1 plus a scalar times v2 and so on. That's a linear combination. But if we're looking at a linear combination of the v's and it's equal to 0, we know that those v's form a linearly independent set, which by definition would mean that each of these scalars here has to equal 0, the scalar 0. That's the definition of linear independence. And notice what that does is it creates a homogeneous linear system. Now think about this for a moment, because we've never, up until this point, used the assumption that we made in the first place, which was that m is greater than n. And here's where it finally matters. So if m is greater than n, then remember the m represents the number of k's that are showing up here. And those k's are the unknowns, right? N corresponds to the number of v's, which is the same thing as the number of coefficients that I'm looking at. That corresponds to the number of equations here. So that means if m is greater than n, then I have more unknowns than equations in this homogeneous linear system. And as we've seen before, that implies that this has infinitely many solutions. In particular, it will have non-trivial solutions, which means there are non-trivial solutions for this linear combination, which means that our set of w's is linearly dependent. That finishes that part of the proof. Okay. The proof of part B, like I say right here, is similar. We omit that part. It's not worth going through all of that again. And notice, again, that we don't really even use the inequality that we would be assuming in the first place, m is less than n for part B, until we get to this very last step down here. So most of this would look pretty similar. The only difference, though, is in part B, I'm trying to prove that the set of w's wouldn't span V if m was less than n. And for the sake of spanning, instead of getting a homogeneous linear system, I'm going to get a general linear system, B1, B2, and so on and so forth. And what's going to end up happening in that case, the reversal of this inequality is going to mean I have more equations than I do unknowns. But to reference something that we've seen in this section already, let's see, that would have been back, not here. Over here, Remember when we solved this linear system in a previous video, we had more equations and unknowns in that case? That guarantees a row of zeros, right? And that row of zeros is what gave us a condition that needed to be in place on this column vector in order for us to have a consistent system. And that condition is going to prevent this from being consistent for all choices of these b's, only the choices that fit that requirement. And so the end result there is that this row of zeros actually implies that this set does not span our vector space. Remember how we said this had too few vectors? This is the case where m is less than n. Okay, so again, not going through a formal proof on that, but that's going to be it for that theorem and for 4.5.